Welcome back everyone. In this lecture we will see the Engel's theorem and Lee's theorem's proofs. Okay. So, let me begin with recalling the invariance lemma that we actually saw last time. So, I will briefly actually explain the core idea in the proof, because invariance lemma plays a vital role in both the Engel's theorem and Lee's theorem proofs. Okay, here is the statement. Let G be some linear Lie algebra. So, this V is non-zero finite dimensional vector space over complex numbers, okay, and A be some ideal inside G. So, then let lambda be a weight of weight for A. So, that means it is a functional, and the corresponding weight space V lambda. So, that is non-zero. So, then you take V lambda, so which is those vectors V in V, such that when you act A on this vector V, you get lambda of A, some scalar times V, which we call it lambda of A for all A in capital A. What actually invariance lemma says, if you take this weight space corresponding to the weight lambda. So, this is called the weight space corresponding to lambda in A star. Okay. So, this weight space is actually, it is easy to see, it is invariant under capital A. The invariance lemma says that this weight space is indeed G invariant. So, then what is the conclusion? V lambda is actually G invariant. So, this is the conclusion of invariance lemma. So, this is what we proved last time. So, we actually just outlined the core idea of this proof, okay, which is actually very important. So, to prove this invariance lemma, we observed the following thing. Okay. You start with some element A in A and then Y in G. Okay. So, then what we needed to prove? So, to prove that this capital V lambda is G invariant, you also take some vector V in V lambda. So, then for this data we need to prove that if you apply Y on V, so then okay, this Y V should be again element of V lambda. So, that means for that A, if you apply it on Y V, we should get lambda of A Y V. Okay. So, this should be true for all A in capital A. So, this equation tells that Y V is again element of V lambda. Okay. To prove that, so what we actually observed, the very first observation is that A Y V, if you use the commutator relation, then this is nothing but Y A V plus bracket A Y V. So, since bracket A Y, which is again element of capital A, as A being an ideal, so this is going to give us this equation. So, lambda of A Y V plus lambda of bracket A V times V. So, in order to prove A Y V is same as lambda A Y V, so we need to only prove that lambda of A V is 0 for all A Y is 0 for all A in A and Y in G. Okay. So, this is the thing we need to prove for all A in A and Y in G. So, in order to do that, what we did, so we wanted to realize this bracket A Y as commutator A Y minus Y A. So, if we are able to actually find a invariance subspace of capital V, so that is actually invariant under both A and Y. So, what is the task? So, the task was find a subspace U of V which is invariant under both A and Y. Okay. So, fix A in capital A and Y in G. So, then this is what we want to buy. And of course, that also should somewhat involve the information that we have started with, that is V in V lambda. Okay. So, that when you do the computation on that invariant space U, especially the computing the matrix of A and matrix of Y and the matrix of the bracket A y on this U. So, that should actually have this information lambda of A y. Okay. For that, what we did, we actually took the smallest invariant space, okay, Y invariant space generated by that vector V. Okay. So, you took U to be the span of C. So, which is V, YV, Y square V and so on. So, we also saw that there is a K such that this will be exactly given by span of V, YV, V, YV etcetera y power k minus 1 V. So, this will become a basis. So, there exists K in N, okay, maybe union 0. So, there is, okay, I can assume to be N such that, so this is a basis. Basis of U. So, then what we actually proved? We proved that for any z, okay, not only for A, for any z, for any z in capital A, this z actually maps U to U. Okay. So, the way we proved, if you take z and apply it on some y or v, then we observe that this is actually equal to some scalar times. Okay. So, let me explicitly write what is that scalar. So, that is lambda z of y power r v plus some term u, where this u will come from the span of v, y v etcetera y power r minus 1 v. Okay. So, this was the computation that we did. So, this is the very crucial computation. So, that was already done. So, basically you have to construct a invariant subspace invariant under both A and Y, which is actually somewhat generated by this V. Okay. So, for that first you start with Y invariant space generated by V. So, and then you just because A being ideal will give us that for any z this U will be invariant. Okay. So, then if then we have seen that if you calculate the matrix of z with respect to the basis. So, for this U, so this is the basis. So, then we saw that this is actually of the form upper triangular with diagonal entries being lambda z. So, this is some in particularly the trace of this z restricted to U is nothing but the dimension of U times lambda z. Okay. So, now when you restrict z to be this bracket A y, which is an element of capital A, since both A maps U to U and Y maps U to U. So, we get the trace of bracket A y restricted to U is 0. On the other hand, you get from the earlier computation, it is dimension U times lambda of bracket A y. Okay. So, that immediately tells you that lambda of bracket A y is 0 for all A in capital A and Y in G. So, this indeed proves, if you go back to our original calculation. So, this indeed proves that A y v is same as Y A v. Okay. So, this is what it proves. So, that is exactly lambda of A y v. Okay. So, we verified this condition. So, this is how we actually indeed proved the invariance lemma. So, now we will actually see various applications of invariance lemma. As a first application, we will prove an elementary fact from the linear algebra. Okay. So, let me state that. So, this maybe you can actually maybe I will state it as a lemma. So, this lemma I am just stating it as a result, this is actually indeed will not be used. Maybe one can use this to characterize nilpotent Lie algebras, maybe I will come to that later. Let me call it this lemma. So, what it says, so you have let us say two operators acting on a vector space V. Okay. So, let x and y, so they are endomorphisms of V such that both x and y commutes with the commutator x y. Okay. So, then one can prove that the bracket x y must be nilpotent. Okay. So, this is some necessary condition to get nilpotent operators. Okay. I will advise you to actually recall various characterization of nilpotent operators. So, which will be useful throughout this course. Okay. For example, one of the characterization says, so how do you prove this? So, to verify the bracket x y is being nilpotent, we need to only check that because we are working over complex numbers, it does not have any non-zero eigenvalue. Okay. So, let us say lambda being eigenvalue. So, lambda being eigenvalue for this bracket x y. So, then we can construct this lambda eigenspace. Okay. This is those vector v in V such that when you apply x y on V you get exactly lambda v. Okay. So, this is the subspace that we are considering. So, now what we can do, we can take this Lie subalgebra generated by x and y. Okay. So, if we take Lie subalgebra generated by x and y, you can see that so it must be, so it must be this subspace. So, you take G, so which is Lie subalgebra generated by x and y. So, since both x and y commutes, so this will be this 3-dimensional space. Okay. So, maybe like I did not actually introduce what is subalgebra generated by some subset, maybe I will introduce this later. Maybe here it is not hard to check, you can take the span of these 3 elements, okay, x, y and then the bracket x, y. Okay. So, this is, we will check, this is actually a subalgebra of GLV. So, if you actually compute the Lie products, okay, so because this is being actually subspace of GL of V, so the Jacobi identity we do not need to worry. So, all we need to verify is the successive brackets should be inside. Okay. So, let us check whether those brackets are again inside G. So, for example, if I take x and y and then take the bracket, so it will be again inside there. Similarly, for y x. So, now all we need to check what will happen if you go further up. Okay. For example, if you take x x x y, since x and x y commute, so this is 0, and similarly what will happen, the y x y again that is 0. So, that is the given hypothesis. So, now in particularly if you take further anything, so there is nothing actually more. So, this computation tells us that G is a Lie subalgebra of GLV. Okay. Now, it is clear that this span of this single element x y, so this is actually is an ideal inside G. Okay. Because if you take any element here, that actually leaves this subspace invariant by adjoint action. So, that means we can use the invariance lemma. So, what invariance lemma says, for the ideal, if you take this lambda eigenspace. Okay. So, that is the weight space. So, for this capital A, this W is nothing but lambda, okay, weight space. So, in particularly both x and y leaves W invariant. Okay. So, now you can see that since both leaves x and y both leaves W invariant. So, if you compute trace of the bracket x y on W, so then this has to be x restricted to W times y restricted to W minus y restricted to W times x restricted to W. So, that implies the trace must be 0, restricted on W must be 0. But on the other hand, what is W? W is lambda weight space, okay, or lambda eigenspace. So, that means this x y acts as scalar. So, if you compute the trace on the other hand, that will be dimension W times lambda. So, that is nothing but the trace of x y on W, but our computation says this is 0. So, that implies lambda must be 0. Okay. Since lambda eigenspace, so W must be non-zero. So, that means lambda must be 0 using this equation. So, this proves that bracket x y must have like only 0 eigenvalues. So, that means the bracket x y must be nilpotent. So, there are other ways to prove the same result. Maybe you can take it as a challenge to prove the same result using some elementary linear algebra results. Okay. So, I will leave it to think leave it to you to think about it. So, let us now see more applications of our invariance lemma. So, you can see that already invariance lemma is somewhat very nice. So, there are so many interesting facts one can prove using invariance lemma. Okay. So, now let us actually prove Engel's theorem, but before getting into the original statement of Engel's theorem, so which I actually wrote it as E1. So, what is E1? So, the first version of Engel's theorem. So, if you take, so let G be a finite dimensional Lie algebra over complex numbers. So, then the first statement says, so G is nilpotent if and only if all elements are add nilpotent. Okay. That means add x nilpotent for all x in G. So, that is same as saying all elements of G are add nilpotent. So, we already proved one way. So, this part is actually obvious. So, which we verified. So, we already verified. So, we need to prove the converse part. Okay, we will see later. So, if you think about it, okay, so this fact actually can be derived from the following fact. Okay, so which I actually called it as E2. So, G is now take it to be a linearly algebra. Okay. So, then so if you have this hypothesis, okay, so all elements of G are nilpotent as operators on, okay, capital V. So, then we can prove that G is nilpotent Lie algebra. Okay. But if you think about it, the converse of this E2, this is actually not true. Okay. So, for example, there are some nilpotent Lie algebras, okay, even linear Lie algebra. So, the trivial example, okay, the converse of E2 is not true. So, what I mean by that, we can easily produce an example of linear Lie subalgebra which is nilpotent, but there is no way to conclude that the elements of G are nilpotent. So, for example, what we can do we can take as an example just C times identity, okay, inside this GLV. So, this is the identity n by n identity matrix. So, then you can see that this is actually one dimensional Lie algebra, okay, because I n commutes with I n. So, this is identity matrix. So, clearly this is actually one dimensional abelian Lie algebra. So, that means this is nilpotent Lie algebra, okay, but there is no basis inside capital V for which this I n is actually like strictly upper triangular. So, in particularly it can be easily verified I n is not nilpotent. Okay. So, it is clear that I n is not nilpotent operator on capital. Okay. So, this is actually a slight warning. So, this E2 only the one way is true, like if we assume that G is linearly subalgebra and then all the elements are nilpotent, then we only get G is nilpotent, not the converse. So, if we think about it, okay, this version E2 actually follows from the following version. Okay. So, there is this E2 dash, okay, which is what we actually prove. Okay. So, you start with a vector space, again you assume to be non-zero space. Okay. So, and let us say G is sitting inside GLV, which is Lie subalgebra. Okay. Suppose each element of this G is nilpotent linear transformation on V. Okay. So, assume that each element of G is a nilpotent transformation, okay, of V. So, then what we can prove, we can prove that there exists a basis capital B of V such that, so each element of this G, okay. So, if you take the matrix of X with respect to this basis B, okay, for each element of, okay, for all X in G. So, this matrix X with respect to B. So, this will be strictly upper triangular. We say this dimension of V is here, okay, and this is true for all X in X. So, you have a common basis B such that the matrices of each element of G with respect to this basis will be strictly upper triangular. Okay. So, this is actually you can call it as a structure theorem of finite dimensional nilpotent Lie algebras. Why? Because we have actually we indeed realize that any linear Lie subalgebra, any linear Lie nilpotent subalgebra as a subalgebra of this strictly upper triangular matrices. So, we already saw that any subalgebra of this strictly upper triangular matrix must be nilpotent, because that strictly upper triangular matrix is itself nilpotent. Okay. So, we are indeed in some sense proving the converse. But of course, I am lying a bit, because we are not proving the converse as like as I stated, because if you start with an arbitrary Lie algebra, Okay. So, then what happens, so far we have seen that only modulo the center we can embed that Lie algebra inside some general linear Lie algebra. So, that is exactly comes from the adjoint representation. So, G modulo the center G will be isomorphic to add G. So, but at least modulo the center, this E2 dash tells you that you can realize that as if G is nilpotent, then G modulo center G can be realized as subalgebra of the strictly upper triangular matrices. Okay. So, that is what we can say from whatever we have proved so far. So, now what is the motivation for this actually? So, the motivation is actually comes from actually one dimensional example. So, if you start with some x in endomorphism of V, you can take G to be Cx. Okay. This is an abelian Lie algebra. So, then if x is nilpotent, then what will happen? So, then you can look at the Jordan form of this x. Okay. So, there exists a basis. So, this is the Jordan canonical form. So, there exists a basis B such that the matrix of x with respect to the basis will look like strictly upper triangular. Okay. So, actually we don't need to really use Jordan canonical form. This can be proved just using induction on the dimension V. Okay. So, I will leave it to you to check this fact. This is an easy fact from linear algebra. So, now let us see how one can prove Engel's theorem. So, to prove this version E2 dash, so it is very clear E2 dash is actually giving you this E2, okay, and E2 and E1 are equivalent. Okay. So, now in order to prove this E2 dash, we will actually make another proportion. Okay. So, that proportion is actually somewhat going to tell you like so whatever I stated in E2 dash is true. Again you take V to be non-zero and then G is being inside GL of V such that each element of G is nilpotent linear transformation of V. Then what we can prove? So, if you take nilpotent operator, what is the important fact about the nilpotent operator? The kernel of that operator is always non-zero. That means 0 is always an eigenvalue, and we have seen in linear algebra the only eigenvalues are actually 0. So, that means one can expect in this case, if you want to prove that this can be embedded inside strictly upper triangular matrix with respect to some basis, then if you look at this strictly upper triangular matrix, the very first 1/1th place, the corner, so that will be 0. So, that means some basis vector of this B, so that should be annihilated by all the elements of G. So, that is what we are getting. Okay. So, that is what one actually expects, and that is what this proportion actually tells us. So, if you start with a non-zero vector space G inside GL of V satisfying our hypothesis, then we can prove that there exists a non-zero vector V in capital V such that each element of this G will kill that vector. Okay. So, this is one can actually so using this proportion it is easy to prove that whatever I stated in E2 dash, maybe you should take it as exercise and then try to do. So, for time being let us assume this proportion. Let me tell you like our outline how one can prove E2 dash from the proportion. So, if you have a vector V which is non-zero vector from capital V such that this x V is killed is 0 for all x in G, then what you can do? You can actually take this W, this is those vector inside V such that x V is 0 for all x in G. Okay. So, then this is a non-zero space. Okay. So, then what you can do? You can actually simply take V modulo W. Okay. This V modulo W, the dimension of this is actually goes down. So, the dimension of this is strictly less than the dimension of V. So, now what you can do, you can use induction on the dimension of V to prove whatever you needed. So, for that what we need to do, we need to actually see that. So, each x in G actually induces a map, okay, which we can call it x bar. So, for each x in G, so there is a map x bar that is actually defined from x modulo V modulo W to V modulo W. Basically how it is defined, you take x bar and then apply it on some u plus W. So, this is just x u plus W. Okay. So, this is a well defined map. Why? Because suppose u plus W is same as u dash plus W, then that will imply that u minus u dash is in W. So, that would imply that x actually will kill this u minus u dash. So, that means x u is same as x u dash. Okay. So, that means you get x u plus W is same as x u dash plus W. So, there is this natural induced map x bar from V modulo W to V modulo W. If x is nilpotent, then it is easy to see that x bar is also nilpotent, okay, that I will leave it as exercise. So, since x is nilpotent, so that implies x bar is also nilpotent. So, now basically you consider this G dash, which is those x bar such that x is coming from G. So, where x bar is inside this endomorphism of GL of V. So, GL of V modulo W. So, it is easy to see this is again actually a Lie subalgebra of GL of V modulo W consisting of nilpotent operators. So, by induction on this dimension of this vector space, so we conclude that there exists a basis. So, there exists a basis B of V modulo W such that, so this x bar with respect to this basis lives inside, okay, this looks like upper triangular, maybe I will write the matrix. So, this is just strictly 0 and then star. Okay. So, now if you list this V as some V 1 plus W etcetera, some V k plus W. Okay. So, then you can see that you can actually take a basis of V basis of W and then you can also take this V 1 etcetera V k, put together you can make a basis of V. Okay. So, start with the basis u 1 etcetera u r of W. So, then one can check u 1 etcetera u r and then V 1 etcetera V k. So, that forms a basis of V. So, now if you just look at the way actually we have chosen u i's. So, this x u I will be 0 for all x in G, okay, and then this x v I, okay, for example, x v 1 will be 0, okay, that means this belongs to actually W. So, that is just a span of u 1 etcetera u r. Okay. So, that means x v 1 is some a 1 u 1 plus etcetera plus a r u r, and similarly x v 2 will be equal to. So, this is the matrix 0 star 0 0, okay, 0 etcetera star star 0, like that the matrix looks like. So, this x v 2 will be some scalar times v 1 plus, okay, some elements from W and then some b 1 u 1 plus etcetera plus b r u 1, because the difference lies inside W and so on. Okay. So, that means if you arrange it in this way, so you can easily see that. So, this basis that you have actually constructed, which is U1 etc. UR and then V1 etc. Vk. So, with respect to this basis, each x looks actually upper triangular. Okay. So, that is very clear from the construction. So, these ui's are all 0. So, this first part, okay, if you write this matrix, so the if you call it u1 ur v1 etc. vk, u2 ur v1 etc. vk. So, this part of the matrix will be 0 and the second part. So, x v1 is already a1 etc. ar. So, that will be filled here, but this is r plus 1. Okay, this part up to this part is 0. So, then if you look at x v1, this is all 0 and this entry is also 0. So, this is actually stable. So, if you go to V2, so the V2 will be, so this is all some entries up to here and then this part is 0, because if you look at this, there is no V2 here and here there is no V1. So, that is why you are getting actually strictly upper triangular matrix. So, this is some elementary fact from linear algebra. So, that you will be able to check comfortably. For example, this is also one can check by the following fact. Okay, the dimension of V modulo W will be exactly dimension of V minus dimension of W. So, in particularly, so the number R plus K will be exactly equal to dimension V. Okay. So, all you need to check, this is actually linearly independent. So, that is also easy to check, maybe just I will write it as, suppose alpha 1 u1 plus etc. alpha r u r plus etc. beta 1 v1 plus etc. beta k v k. If this is 0, then what you can do, you can just go modulo w, okay, just to go modulo w, then this equation will give you immediately beta 1 v1 plus w plus etc. plus beta k vk plus w, this is 0. So, that implies that beta i's are all 0, because v1 bar etc. vk bar, that is actually a basis for the quotient. So, then that would imply alpha 1 u1 plus etc. plus alpha r ur is 0. So, again ui's are all basis for w. So, that would imply that alpha 1 alpha j is 0 for j equal to 1 to r. So, this proves that if you have a linear Lie subalgebra, okay, inside your GL of V, such that each element of this linear Lie subalgebra is nilpotent linear transformation on V. So, then using this proportion one can get a vector, non-zero vector such that annihilated by all elements of G. So, using this and by induction on the dimension of V, we will be able to construct comfortably a basis of capital V such that with respect to that basis, each element of G looks like strictly upper triangular matrix. So, basically modulo this proportion, we have actually proved this Engel's theorem. So, maybe I will stop here because we are running out of time. So, I will continue the Engel's theorem proof in the next class. Thank you.